Hello students, today I am going to teach you time domain specifications. Right, the transient response of control system is determined by time domain specifications. Here the transient response of control system is characterized by time domain specifications. You see that this is transient response. Right, so this transient response is characterized by time domain specifications. What are the time domain specifications? Rise time, peak time, post delay time, maximum peak overshoot, and settling time. So these are the time domain specifications. Now we see the unit step response curve. All right. So this is this is a unit step response curve showing time delay, rise time, peak time, maximum peak overshoot, and settling time. So these parameters, these time domain specifications, so will be characterized by the time domain specifications. We see we just observe the unit response curve here showing. So the first one is the delay time. So what is the delay time? Delay time means the delay time is the time required for all the response to reach half the final value that very first time. Okay, you see that the response curve of final value reached 50%. So this one is, so this is time delay. This is time delay. This response, this time taken to reach 50% of final value is called the time domain. So next we see the rise time. So rise time, what is the rise time? You see the rise time from point from 0 to from till this point. You just remember first to see the graph here. So this is the this is in time domain. So this is the C of t. So this is C of t. This is a response curve. So this is input signal. So this is input signal, means is a step signal given to the system. When your system is subjected to step signal, so you got this underdamped response. Okay, underdamped response you got. So you see that here this your response is between 0.5% is 5% is tolerance. So 5% means plus or minus 5%. It means it is 0.95. So above plus 5 is 1.05, minus 5 is minus 0.5. Okay, so you see that what is the rise time? Rise time means the rise time is the time required for the response to rise from 10% to 90%. Okay, again 10% to 90% to 95% or 0 to 100% of the final value. Okay, so there are three ranges here. The first one is here. You see that the time taken to reach the final value. Okay, of rise time, how much it is? So from 10% to 90%. So this time taken, the response is called rise time. Okay, how much time is taken from 10% to 90% is called time. This is called a rise time. Okay, and also 10% to 95% also we call it a rise time. Okay, and also 0% to 100% also we call it a rise time. So for underdamped second order system, 0 to 100% rise time is normally used. Okay, what you should remember? So for underdamped means what? This is underdamped. This is underdamped. Okay, in this case, all right. So the rise time is taken at 0 to 100%. It's normally we have taken. So overdamped second order system, the 10% to 90% rise time is commonly used. So overdamped means this is a overdamped. This is overdamped, right? This is overdamped. Okay, this is overdamped. So normally taken 10% to 90% rise time is commonly used. Um, so here underdamped second order system, 0 to 100% rise time is normally used. So here underdamped means, so this is underdamped response. In this response, rise time is taken as 0 to 100 percentage. Okay. So next we see what is the peak time. The peak time is the time required to reach the first peak of the value. You see that the time taken, so to reach the peak value from here to here. So how much time is taken to reach from 0 to this peak is called the peak time. So we can also represent from this point to the length from here to here. So the time is taken from 0 to this peak is called peak time. Okay, this is the peak time. Next is the maximum peak overshoot. Next is the maximum peak overshoot. So next we see that maximum peak overshoot, uh, it is defined the ratio of the maximum peak to the final value. If you just see the diagram here, so maximum peak overshoot, for the definition, it is defined the ratio of the maximum peak value to the final value. So this portion is maximum peak overshoot. So from this point to this point, so this portion is a maximum peak overshoot, right? Maximum peak overshoot. So it is defined the ratio of maximum peak value. So ratio of maximum peak value to the final value. Okay. So the formula is here. The formula is maximum peak overshoot is equal to CTP. So that is peak overshoot. Minus final value. Okay. Minus final value to the final value. So maximum peak value is measured from final value. So maximum peak value is measured from the final value. Final value means when you see the graph. So this is when you see this graph, this response, so it is oscillating, and the finally dampings are being died out. So so that when once to settle, so that we take as a final value. Okay, see here you see that when t is equal to infinity, it means it reaches the steady state. So c of infinity is equal to final value of c of t. CTP is a maximum value of CP. So this from the point to this to this is called a minimum value of c of t. So next we are going to see what is so next we see settling time. Settling time as a T of S, it is defined as the time taken by the response to reach and stay within a specified error. It is usually expressed as a 10 percentage of final value. Settling time, it is usually expressed as percentage of final value. We see that this step response. So it is defined the time taken by the response to reach and stay within the specified error. If you see that see this graph, this is step signal. Okay, So this is 90 percentage. What is the 90 percentage? We just see that this is 95 percentage, right? And this is 0.95, this is 1.05. This is because 5% is tolerance, okay, plus or minus 5% tolerance, okay, plus or minus minus 5% means it will come 0.95. 5 plus 5 means 0.5 percentage. You see that settling time means it is defined as the time taken by the response to reach and stay. So you see that to reach and stay, to reach and stay. See, so this response, so it is response is reaching and staying, okay, staying. So in a specified error, you just see, observe it from here, so this is going away from this point, this peak overshoot. This also below that, this also above this line, and specified error, and here also below that. After that, from here what happened, it is within the specified error, so it will not go away, okay. After some time, so what happened, you see that this is settling time. After some time, you see that there is a small gap between this, so this is actually called steady state error. Steady state error when t approaches to infinity, okay. Once again you observe, this graph. Settling time means it is defined as a time taken by the response to reach, it is reaching. So you see that here, reaching, how much time is taking to reach in a specified error, okay, and staying within a specified error, okay. So yes, once again I'm showing, this is your step input, okay. Your response, so your response is so oscillating like this, and finally, so it is reached the final value and staying within the specified error. So if finally at this, it is settled at this point, so what happened, you see that this is a step signal, okay, this is output. So this portion is called steady state error. So when t approaches to infinity, so this is actually from this point to this point is called settling time. This is settling time. So it is reaching in so it is reaching, so it reach and stay within a specified error. You just see that when you taking settling time as, so it is reaching C, so it is above this this portion, so here also below that, this also above. But when you come to this, it is reaching, okay, and it is staying within a specified error, so that is called steady state error. So there's a few comments on transient response. There are a few comments on transient response. So the first one is, except for a certain applications where oscillations cannot be tolerated. So it means except certain applications, okay, where oscillations cannot be tolerated. So this kind of response, oscillations, this kind of response cannot be accepted, it cannot be tolerated, okay. This kind of response will make a problem. But it should accept certain application. I have told you last time, so residential room heating system, okay, that there we are using enough temperature control systems, so there the output of the control system is oscillations. So that kind of applications, so this oscillation is acceptable, okay. And second thing, so it is desirable, okay, that the transient response be sufficiently fast. It means what is desirable? You see this transient response, okay, be sufficiently fast. It should be fast response and be sufficiently damped. And sufficiently damped means it should not be over damped. It should not be over damped like this. Sufficiently damped. This is another condition. Next, thus a desirable transient response of second order system, the damping ratio must be between 0 to between 0.4 and 0.8. So desirable transient response of second order system, damping ratio. So damping ratio G between 0.4 and 0.8. You know that if you just take a response, so as damping ratio becomes small, so what happened, this peak will increase. This peak will increase. You just see that. And we have seen this is, if you take this one, so this is, if damping ratio is 0.1, so more oscillations. If damping ratio is 2, so it is little oscillations. If damping ratio is 3, so it is less oscillations. So when damping ratio is 1, so it is critically damped. If damping ratio is more than 1, so it is this is the response is very sluggish, over damped. So the desirable transient response second order system is should be damping ratio between 0 to 4. So that's a desirable transient response for second order system. So small value of zeta, it means 0 zeta value less than 0.4 yields excessive overshoot in the transient response, and a system with a large, so more than this, what happened, the response will sluggish. As I told you, if your damping ratio is very large, more than this, what happened, the system is very sluggish. It may have a chance to have a more error, and the system is very sluggish, so the response is very slow. So this is a few comments on the response specifications. So next we are going to derive expression for time domain specifications. Okay, expressions for time domain specification. Okay, so first expression is rise time. That is TR. So we are going to derive expression for rise time. So you see the graph. When you see the graph, so here this is the graph. Okay, so this is our step signal, right? So this is a response. So response. So this is a rise time. The rise time is from this point to, so this is called rise time. From this point to this. Okay, so I'm going to derive expression for the rise time. So I already have given definition also. So you know that the response of underdamped system. What is the response of underdamped system? C of t is equal to 1 minus e raised to minus damping ratio omega n by root 1 minus zeta square sine omega dt plus theta, right? So you know this formula, we have derived expression for this response. Okay, so this equation is expression for this response. Okay, from this response we are going to find the rise time. Okay, the TR we are going to find it. So how we are going to find the TR? So first what you have to do, at t is equal to TR, you see that here at this point t is equal to TR. Okay, and you just make CT is equal to CT P is equal to 1. You see that this is the 1. So when your response reach from 0 to here, this point. Okay, so what is our what is the value of t here? T is equal to 1. Okay, that's why I make a CTP is equal to 1. Okay, at this point rise time is equal to 1. Okay, now we substitute in this equation. Okay, here CTP is equal to, okay, wherever t is there is substitute, sorry, it is TR. Okay, so it is not TP, this is a TR. Okay, so wherever t is there is substitute, here also TR, wherever t is there is substitute TR. Okay, so in place of t I substituted TR. So what is the equation? 1 minus e raised to damping ratio omega n t by, so 1 minus zeta square, okay, sine omega dt plus theta. Okay, here also we can substitute t is equal to tp, but we will substitute at the end. Okay, what is CTR? CTR is equal to 1, so we substitute in this place 1. Okay, so 1 minus e raised to minus zeta omega n t by, here also root 1 minus zeta square into sine omega dt plus theta. Okay, this plus 1, this 1, so gets cancelled. So what is left? It is 0. So even a minus also you can send this side, so that become plus. So e raised to, finally you have left this is equation, damping ratio omega n t by 1 minus zeta square root, so sine omega dt plus theta, right? Okay, so now what we do, so now what I'm going to do, see here this one also we can send this side, so root of 1 minus zeta square also we just cross multiply, 0 into this value become 0, so 0 is equal to e raised to minus zeta omega t sine omega d t plus theta. So you know that here e raised to minus zeta omega n t is not equal to 0, is not equal to 0. Okay, and sine omega dt plus theta is equal to 0. When it is 0, when it is 0, so I'm taking this one as a pi, so pi is equal to 0, pi, 2 pi, right, and 3 pi. Okay, then what happened, what happened here, omega dt plus theta become pi. Okay, so even you substitute omega t plus theta 0, so what happened is sine 0, so in place of omega dt plus theta I'm going to put 0, so what happens, sine 0 is 0, sine pi is 0, sine 2 pi is 0. Okay, so now I'm going to take t as a rise time tr, t is equal to tr, so t is equal to tr I'm substituting here. So now what happened here, so omega t omega t is equal to, what is omega d, tr is equal to 5 minus, if theta bring that side, become theta. So tr is equal to, so 5 minus theta by, okay, omega t. So this is the raised up expression, and also we can write raised term. So tr is equal to, so this is 5 minus, so omega d means here omega n, okay, so root zeta 1 minus zeta square, 1 minus zeta square. So this also we can add as an expression. You know that this theta is equal to what? Theta is equal to tan inverse root 1 minus zeta square by zeta, okay, zeta, okay. This is also, you know this equation, okay. So this is expression for rise term, this is expression for rise term. Next we are going to derive expression for peak time overshoot. Next we are going to derive expression for peak time overshoot, okay. So now we are going to derive expression for peak time, okay. So this is a expression for peak time. So peak time generally we are going to represent as a TP. So you just see the graph here. So this is a C of t, this is output, this is a extent time. So you know you have this, this is your step signal. So this is a 1 unit step signal, okay. So you see the your response, okay. This is peak time, okay. So it is reaching from this point to this is called a peak time, okay, peak time. So we are going to derive expression for the peak time. So how we are going to get the expression? First to differentiate C of t, differentiate C of t with respect to t, differentiate C of t with respect to t and equal to 0, and equal to 0. It means your differentiate, so differentiate with C of t, you differentiate with respect to t, and okay, and you substitute here t is equal to tp. So you know that here t is equal to tp and make is equal to 0. So this is the clue, okay. You have to substitute here, you differentiate. You know what is C of t? C of t, you know, right? C of t is equal to under damp response 1 minus e raised to minus zeta omega n by root 1 minus zeta square, right? So sine omega dt plus theta, okay. You know this expression, so you have to differentiate this one, okay. So I'm going to differentiate it, this one, okay. I'm going to differentiate it. So I'm going to differentiate, so dy by dt. So what is ct? Ct is equal to 1 minus e raised to, okay, minus zeta omega n t, here supposed to be t, by root 1 minus zeta square sine omega dt plus theta, okay, and is equal to 0, okay. So when I differentiate, so it become 0. When differentiate concept it become 0. Now it look like this is u, okay, this is v. You know the uv formula. What does uv formula says? So dy by dx u v. So you know this formula, just substitute in this formula. So what is u here? U is equal to this value, so v is equal to sine omega dt plus theta. So now we differentiate. When you differentiate, so 0, differentiate 1 0, so minus. So when you differentiate u, so this is u, so what happened, this is root of 1 minus zeta square is a constant, so 1 minus zeta square constant. When you differentiate e raised to minus zeta omega n t, again we are going to differentiate this one, so you want to get minus zeta omega n, you get, so into sine omega dt plus theta. So when you differentiate this one, okay, now we are going to derive expression for peak time. So we have seen that d by dx u p is equal to u dash v plus v dash u. You know this formula, right? So so to differentiate 0, so when you differentiate, so what you get, dy by dx, so here dt, so e raised to minus omega damping ratio omega n t, okay, by 1 minus zeta square root 1 minus zeta square into sine omega dt plus theta, okay, plus dy by dt sine omega dt plus theta into e raised to minus zeta omega n t by root 1 minus zeta square, okay. So then next, so when you differentiate, so what you get, when you differentiate this, so this is 1 minus zeta square, right? When you differentiate this one, e raised to minus zeta omega, when you differentiate, you will get minus zeta omega n, okay. So after differentiating, again we have to differentiate this value. You know that d by dx e power ax is equal to, okay, e power ax, again you differentiate, you will get a, okay. So this is a formula, you know that, okay, this is a formula, you know, okay. So now differentiate this one. Now dy by dx sine omega dt plus theta. So what happens? So that is a cos omega dt plus theta, okay. Again you have to differentiate this one. So dy by dx sine t, dy by dx sine x is equal to cos x. You have know this formula. Again you differentiate this omega dt plus theta, so you will get omega d, right? So this term you have to keep it same as it is. Right. So now, so 0, so what happened, minus zeta omega n e raised to root 1 minus zeta square, okay. So cos should be multiplied here, sine omega dt plus theta, okay. So sine omega dt plus theta plus theta, so plus cos omega dt plus theta into omega d into e raised to minus zeta omega n t y, okay, root 1 minus zeta square, root 1 minus zeta square, okay. So 0, um, 0 what do you do next? So next you omega d is there, so omega d you have to write omega d is equal to omega n root of 1 minus zeta square, that you have to write here. And also I'm going to take a common here, e raised to minus j omega n I'm going to take as a common, okay, minus e raised to j omega n. So you see that this I'm going to take as a common, this term, and this term I'm going to take as a common, also it's minus, and this term also I'm going to take as a common. When you take this common, so you will get 1 minus root 1 minus zeta square sine omega dt plus theta, right, then minus cos omega dt plus theta, right, omega d by 1 minus root 1 minus zeta square, 1 minus zeta square. So now 0, so you write omega d is equal to, so you know that omega d is equal to omega n into root of 1 minus zeta square, you know that value, okay. So e raised to minus zeta omega n, okay, 1 minus zeta square sine omega dt plus theta, okay, minus cos omega dt, okay, plus theta. So I'm going to write omega n, so 1 minus root 1 minus zeta square, root 1 minus zeta square, this both gets cancelled, this both gets cancelled, okay. So next, so now what I'm going to do, now I'm just cross multiplying this equation, cross multiplying this equation, okay. So 0 e raised to minus zeta omega n, okay, it's minus is there, just you take LCM. So what happens, sine here we missed this term, zeta omega n, so zeta omega n, right, zeta omega n sine omega dt plus theta, okay, so minus cos omega dt plus theta omega n into 1 minus zeta square, minus zeta square, 1 minus zeta square, okay. So now what you do here, and here also omega n is there, here also omega n is there, so you can take it outside, so 0, so here is root of 1 minus zeta square, so here also omega n, see that here also omega n, here also omega n, so you can take it out outside, so you get e raised to minus e raised to zeta omega n into omega n, so this is also I'm taking outside, root 1 minus zeta square, so is equal to so sine delta sine, so this is damping, this is sine omega dt plus theta minus, so 1 minus root 1 minus zeta square cos omega dt plus theta. Okay, so this expression is there. So we'll continue with this. So next what will come? So this is 0 is equal to 0, then minus omega n e raised to minus zeta omega n t, right? So root 1 minus zeta square. So sine omega t plus theta, okay, zeta minus, okay, so then root 1 minus zeta square cos omega dt plus theta. Okay, we have formula. What the formula? We have zeta, we have formula zeta is equal to cos theta, okay, root 1 minus zeta square is equal to sin theta. So you have these two formula. Substitute in place of zeta, we substitute cos theta. In place of root of 1 minus zeta square, we substitute sin zeta. So what you get? So 0 minus omega n e raised to minus zeta omega n t root 1 minus zeta square, okay, so sin omega dt plus theta, what is the zeta value? Cos theta, okay, minus, so this value become so this value become sin theta. So we have a formula sin a into cos b minus cos a into sin b is equal to sin a minus b. See, formula is sin a into cos b minus cos a into sin b is equal to sin a minus b. So you have to apply this formula. So when you apply this formula, so you will get, so what you get? 0, okay, e raised to minus omega n e raised to minus so 0 into minus omega n, okay, e raised to minus zeta omega n t by root 1 minus zeta square. So sin a into cos b, cos a into sin b is equal to sin a minus b, okay, plus minus gets cancelled. So what is left? So I can even this term I can cross multiply here. So minus omega and also cross multiply. So this term become 0. So finally I'm going to write like this. So 0 e raised to minus zeta omega n t sin omega dt plus omega dt, only omega dt. So this you can cross multiply this side, and after that 0 into root 1 minus zeta square is 0. Again 0 by minus omega n is as also 0. So finally you get this expression. Okay, so here I see that omega dt is equal to, I'm going to substitute as a phi. Okay, if phi is equal to 0, what happened? If phi is equal to 0, it means you substitute in place of omega t is equal to 0, sin 0, what happened? 0. And again you substitute pi, sin phi 0, again sin 2 phi 0, sin 3 phi 0, and so on like this. Okay, so what I'm going to do here, e raised to minus 3 and zeta omega t is not equal to 0, and sin omega dt is equal to 0. So when it will be 0? When omega dt is equal to 0 or pi or 2 pi. Okay, so first I'm going to take only this term. So sin omega dt is equal to pi. Omega dt is equal to pi. Okay, so from this equation, So what is you are going to find? You have to find expression for you're going to expression for the peak time. Okay, now here T is equal to Tp. Okay, so what I'm going to substitute here, omega dt is equal to Tp is equal to pi. Okay, in that case Tp is equal to pi by omega d, pi by omega d. So and also we can write Tp is equal to pi by omega d means omega n root 1 minus zeta square. So this is the expression for peak time. Expression for peak time. Okay. So next we are going to derive expression for maximum peak overshoot. Maximum peak overshoot. Next we are going to derive expression for maximum peak overshoot. Maximum peak overshoot, that is MP. Okay, you know that percentage of MP, the formula is CTP minus C infinity, okay, by C infinity into 100. So you just substitute from this expression. I'll substitute from this expression. What expression we have? E raised to we have the expression C of t is equal to 1 minus e raised to minus zeta omega n t by root 1 minus zeta square sine omega dt plus theta. Okay, here what happened? We substitute t is equal to Tp in this equation and t is equal to infinity. First I'm going to substitute t is equal to infinity. When you substitute t is equal to infinity in this equation, what do you get? C infinity, okay, C infinity 1 minus, okay, if we substitute infinity here, what happened? This whole term become 0. Okay, so what do you get? C infinity is equal to 1. C infinity is equal to 1. So next we are going to substitute t is equal to Tp. Okay, so CTP, you have to find CTP, C infinity, and finally you can substitute. Okay, CTP is equal to 1 minus e raised to minus zeta omega n. T means here, what is T? T means Tp. Okay, maximum peak overshoot means you just see the graph here. So graph, you know that T, this is C of T, and your step signal is this. Okay, and you have this kind of response. So what is the maximum peak overshoot? The maximum peak overshoot is this one. So this portion is maximum peak overshoot. In percentage we are going to find it. Okay, this portion is maximum peak overshoot. We are going to find the expression for this. So see, this is a TP and this response is reached infinity. So that is C infinity. This is a CTP, okay, and this response, final response is C infinity when t approaches infinity. Okay, so now we substitute in place of t, substitute Tp. Okay, so root 1 minus zeta square sine, so omega d. So in place of t you are going to substitute Tp, okay, plus theta. Okay, so CTP is equal to, so 1 minus e raised to omega. What is Tp value? Tp is equal to, you know, pi by omega d. We have derived the expression for peak time. Peak time, Tp is equal to pi by omega d. Expression. This is expression for rise time. Okay. So plus theta. So omega d gets cancelled. So what is left? Zeta omega n Tp root 1 minus zeta square. And we left with the sine pi plus theta. What is sine plus theta? Sine plus theta is equal to minus sine theta minus sine theta. So you know that sine pi plus theta is equal to minus sine theta okay. So when you substitute this here, c of t is equal to 1 minus, okay, so e raised to zeta omega n Tp by root 1 minus zeta square minus sine theta. So minus sine theta. That become minus sine theta. So what is CTP? CTP is equal to 1 plus e raised to minus zeta omega n Tp. Okay. So you know what is Tp? Tp is equal to pi by omega t. Tp is equal to pi by omega t. Okay. So this is substitute in this equation. So CTP is equal to 1 plus e raised to minus zeta omega n. When you substitute Tp 5 by omega t. Okay. Then what happened? CTP is equal to 1 plus minus omega n. So pi, what is omega d? Omega d is equal to omega n root 1 minus zeta square. So omega n gets cancelled. So CTP is equal to 1 plus e raised to minus zeta phi by root 1 minus zeta square. So this is the CTP value. So substitute, C infinity is equal to excuse me. Alright, what is the percentage? Maximum peak overshoot percentage is equal to CTP, okay, minus C infinity by CTP into 100 in percentage. So MP is equal to percentage MP is equal to, it means maximum peak overshoot. What is CTP? CTP is this value 1 plus e raised to minus zeta phi root 1 minus zeta square minus 1 by 1, okay, into percent. So plus 1 minus 1 gets cancelled. So percentage of MP is equal to, so e raised to minus zeta phi root of 1 minus zeta square into, this is the expression for maximum peak overshoot. This is the expression for maximum peak overshoot. It's the expression for maximum peak overshoot. So next we are going to derive expression for settling time. Next we are going to derive expression for settling time. So settling time, we are going to derive expression for settling time, that is settling time Ts. So we know the graph. So you know the graph from the response. This is C of t and this is t. So this is your given input. So this is your given input. For the given input, and you see that these are the plus or minus, or this is a band, acceptable band. Okay, this is acceptable band. See your response. So see your response. Okay, it's going. So this kind of response. Okay. So this is your response. You see that settling time means, what is settling time? So your response so is reached specified, it is reached the specified band and staying within the error. So you see that, so you see the peak. So it is went into the range. Okay, this point and this point. So from here, so it is not going above this line, and here also peaks are not going below. So this is settling time. So it is stayed within the specified error. You know that specified error, so 5% or 2% is acceptable. Okay, so this is a settling time. So we are going to do expression for the settling time. So the response here, the response of second order, the response of second order system has two components. So what is the first one? So first one is decaying exponential term, and the second one sinusoidal component, that is sine omega dt plus theta. Okay, so your second order response, what is second order response? So your second order response is C of t is equal to so 1 minus e raised to minus zeta omega n t by root 1 minus zeta square sine omega dt plus theta. So this is the second order response. Okay, this has two components. The first component is exponential component, second one is the sinusoidal component. Okay, so now, so the decaying exponential term here, the decaying exponential, term reduce the oscillations produced by sinusoidal component. So this, you see the response, you see that. So this exponential, see this envelope, okay, is reduces the oscillations produced by sinusoidal component. You see that this is gradually it is decreasing sinusoidal components. So what I'm going to do, so t is equal to here, t is equal to ts. Okay, term substitute t is equal to s. So e raised to minus zeta omega n t by. So in this expression, what happened at this sinusoidal will disappear when t approaches to infinity. So only the exponential term is here. So this is equal to 2% and also 5%. So now 2% means I'm going to put 0.05. 0 2. Okay. For the small value of zeta here, you see that for the small values of zeta, so what happened? 1 minus root 1 minus zeta become 1. Okay, it become 1. So it's very small values, we 0.001 like this. What happened? So it won't change much. So root 1 is 1. So now I'm going to substitute root of 1 minus zeta square is equal to 1. So you have only left with, so e raised to minus zeta omega n ts is equal to 0.02. Both side apply ln, natural logarithm. So what you get? So when you apply 0 omega n ts is equal to ln 0.02. Okay, so what happened? This become this ln. So you know that ln e by e is equal to 1. ln is 1. So what you get? Only minus zeta omega n ts. So when you use calculator, when you get approximately, you will get a 4. Okay, so this minus gets cancelled. Okay, so what happened? We need a settling term. Ts is equal to, so 4 by zeta omega n. So this is the expression for settling time. And also you know that 1 by zeta omega n is equal to t. That's a time constant. So I am also can write a settling time is equal to 4t for error 2%. Now we are going to find error for 5%. Okay, 5%. Okay, so when you find the 5%, so what the value will get? So this is, so for 5% error. Okay, so e raised to minus zeta omega n ts, so 0.05. So when you apply ln, so e raised to minus zeta omega n ts is equal to ln 0.05. So this value become omega n ts. So this value become minus 3. So minus gets cancelled. So ts is equal to, so 3 by omega n. So this value become 3t. So ts is equal to 3t. So generally we write equation like this. So ts is equal to settling term equation ln percentage of error by 3 omega n. So this is the final expression for settling time. Final expression for settling time.